Good day, everyone. So we are reviewing Wetzel's Limnology textbook, the fourth edition, and we just went over the thermodynamic properties of water in chapter 3 yesterday. And today we'll be starting to review the specific heat capacity and latent heat of water. But before we embark in that section, I wanted to go over these figures. There are like 6 figures that shows the property of water with a change in temperature. And so therefore, as temperature increases along the x-axis, the specific property of water is mapped. And so we have 2 types of waters that are mapped. The first type being the pure water, which is the blue curve, and then the salt water, which is defined at 35 grams per kilogram, which is in orange. So the first one is the kinematic viscosity of water. And as you can see that the viscosity of water decreases with increasing in temperature for both salt and pure water. The surface tension follows the same pattern. The surface tension of water decreases with temperature for both pure water and salt water. The isobaric heat capacity, so there's a little bit of a difference between pure water and salt water. So with increasing temperature, pure water, you can see that the isobaric heat capacities, or the capacity of water to store heat, decreases, where with salt water it actually increases slightly. The thermal diffusivity, so the ability of substances to diffuse in water, increases for both salt and pure water. The diffusivity of NaCl, or sodium chloride, or salt, so therefore only salt water is mapped, increases with temperature. And then the saturation mixing ratio in air of pure water increases with temperature. So let's move on to specific heat and latent heat. The isobaric heat capacity of water, or specific heat capacity, the energy required to raise a unit mass by 1 degree C or 1 degree Kelvin at constant pressure for water, is about 4,200 joule per kilogram per Kelvin, and is very high relative to values for most substances. In particular, it is much higher than the heat capacity of rock and soil, typically around 400 to 1200 joule per kilogram per Kelvin, air 1000 joule per kilogram per Kelvin, and ice less than 2100 joule per kilogram per Kelvin. Thus, the daily and seasonal cycle of temperature in natural waters is usually much smaller than that in air above the water and in over the surrounding land surface. In turn, these differences give rise to a wide range of weather conditions where open water exists: daily lake breeze, land breeze effect, milder winters, and cooler summers near the water, fogs that appears in the fall, and in the apparent steaming of the water surface on cold, calm days. The heat capacity of water itself varies slightly with temperature and salinity, so temperature is not conserved under mixing. That is, the temperature of a mixture of waters of different initial temperatures is slightly different from the average of the initial temperatures. However, the effect is small. For example, the final temperature after mixing equal masses of pure water at 0 degrees C and 20 degrees C is 9.98 degrees C. And for most limnological purposes, temperature can be considered an approximately conservative measure of heat. In the oceans, however, best practice for heat content calculation is to use a thermodynamic property called enthalpy, since it is by definition conserved under mixing at constant pressure, or a derived thermodynamic variable defined in TEOS-10 called conservative temperature, based on potential enthalpy instead of the measured temperature. Energy must be absorbed from the environment to convert ice into water. The latent heat of melting is about 330 kilojoule per kilogram, and considerably more must be absorbed to convert water into water vapor. The latent heat of evaporation is 2,500 kilojoule per kilogram. The amount of energy is released for phase changes in the opposite direction. Evaporation occurs when the air above water is undersaturated with warm air, being able to hold considerably more water vapor than cold air. Sudden cooling of moist air can then lead to the formation of fog, clouds, or precipitation in the form of rain or snow. Freezing of surface waters is a complex process in which water molecules form a crystalline, solid structure while rejecting the dissolved salts. The resulting brines have a much lower freezing point and can therefore remain liquid even when surrounded by ice. The presence of these brine pockets makes the properties of sea ice and saline lake ice very different than those of freshwater ice. Transport properties. The transport properties of a fluid govern the rate at which quantities within a fluid are transferred from one location to another. The kinematic viscosity, thermal diffusivities, and molecular diffusivities govern the rate of transfer of momentum, temperature, and dissolved substances, respectively. However, the transfer of forces and heat energy are better described by the dynamic viscosity, which is the product of the kinematic viscosity and density, and the thermal conductivity, which is equal to the product of thermal diffusivity, density, and specific heat capacity, viscosity. The viscosity of water is the resistance it gives to moving objects. The kinematic viscosity of water decreases as temperature increases, and for pure water, the viscosity at 25 degrees C is about half of its value at the freezing point. Salinity increases the viscosity very slightly, although the kinematic viscosity of water is somewhat less than the viscosity of air. Its density is very much greater, so viscous drag forces are about 100 times larger in water than in air. Resistance to movement caused by the viscosity of water is generally most important for the dynamic of macroscopic particles. This is because moving objects are usually surrounded by a viscous boundary layer less than 1 millimeter thick. The motions of larger objects are thus more typically controlled by turbulent rather than viscous drag. Viscous drag is the major determinant of the sinking rate of small particles and the rise rate of small bubbles. Viscous drags also affect planktonic life at small scales, and these organisms have developed a variety of ingenious propulsion mechanisms to overcome its effects. At even smaller scale, temperature-dependent changes in viscosity are the largest, although not the only, source of the temperature dependence of electrical conductivity. Diffusivity. The diffusivity of a substance in a liquid measures the degree to which that substance will disperse. In water, the thermal diffusivity, characterizing the spread of temperature from warm to cold water and vice versa, is approximately 100 times larger than the molecular diffusivity of most dissolved salts in water, which are typically within a factor of 2 or so of that of sodium chloride. Unfortunately, it is not possible to precisely define the diffusivity of a mixture of salts with a single number, as the different ions will not diffuse at the same rate. Salt content in lakes and oceans may then fractionate when diffusion is important. Also, it is important to note that molecular diffusivities, which are a property of a particular substance in a fluid, should not be confused with eddy diffusivities, which are a property of turbulent flow with a particular geometry. Eddy diffusivities in turbulent flows are many orders of magnitude greater than molecular diffusivities and identically affect heat and salt. The larger numerical difference between thermal and molecular diffusivities give rise to a variety of subtle effects in situations where shear-driven turbulence is weak, in water columns where density increases with depth, but the large-scale temperature profile is destabilizing while the salinity profile is stabilizing. The difference in diffusivities can give rise to the so-called double diffusive instabilities. These are spontaneously generated instabilities that change the water column into a highly layered state in which property profiles have a characteristic staircase appearance with steps in both temperature and salinity. These steps are composed of turbulent, well-mixed layers from tens of centimeters to meters in height, separated by thinner, stratified diffusive layers. Such staircases can sometimes be seen near the bottom of lakes with reasonably high salinities and geothermal heat sources, electrical conductivity. If ions are dissolved in a fluid and move under the influence of an applied electrical field, the fluid is said to be electrically conductive. The electric field accelerates the positive and negative ions in opposite direction, resulting in a current flow, but the speed of these ions is also limited by viscosity. Electrical conductivity is the rate of this flow relative to the strength of the applied field and is typically expressed in units of micro or millisiemens per centimeter. As an aside, conductivity is a property of the fluid, but instruments that estimate this property typically measure the conductance, which is the inverse of electrical resistance in a measured cell. Conductance is related to conductivity by a cell constant with units of inverse length whose magnitude can be determined from the geometry of the cell, but is usually quantified by standardization with a solution of known conductivity. Pure water is very slightly conductive due to small concentration of dissolved proton and hydroxide ions. More typically, when in contact with air, the dissolution of carbon dioxide gas and its reaction with water to produce protons, bicarbonate, and carbonate ions give rise to a conductivity of about 1 microsiemens per centimeter in otherwise pure water. A number of small lakes in western North America with very pure natural waters have been found to have conductivities of less than 3 microsiemens per centimeter, approaching this air-saturated limit. The electrical conductivity of natural waters, however, is usually much higher, 10 to 2000 microsiemens per centimeter for lakes, and even higher for seawater, due entirely to the presence of dissolved salts. The magnitude of the conductivity is roughly proportional to the concentration of dissolved salts in all but the most saline natural waters, but the actual scaling factors that relates the two depends on the relative composition of the salt in question. Extremely precise measurements have been made of this relationship for seawater, whose relative composition is constant to a large degree, so seawater salinity estimates are primarily made through conductance measurements using the practical salinity scale. In lake and river waters, however, the scaling factor can be quite different from that for seawater. The mixture of salts in lakes whose dominant anion is bicarbonate is only about 60% as conductive as seawater of the same mass fraction salinity. Other approximate relations of this sort are available for different water types, and a number of attempts have been made to develop numerical models that relate arbitrary chemical composition to conductivity, but for highest precision in a specific lake, laboratory measurements are still required to develop a salinity scale for that lake. Electrical conductivity is also highly dependent on temperature, increasing by about 1.9% for every degree increase in temperature for most salt. This change largely arises from changes in the viscosity. However, this temperature dependence is much lower for the proton ion, which migrates differently than other ions, such using a proton jump mechanism, not really affected by viscosity. So very acidic lake with high concentration of proton ions can have a different temperature sensitivity for their electrical conductivity. In any case, conductance measurements are only a useful proxy for salinity when combined with temperature measurements. Specific conductance is defined by limnologists as a conductance measurement that is both calibrated and corrected for the effect of temperature, usually to a temperature of 25 degrees centigrade, and is then widely used measure of salinity as specific quantities usually imply only a normalization to unit masses or volume. A better but less used term for this temperature corrected measurement is reference conductivity. Conductance measurements do not, however, account for the presence of non-conductive elements such as silica or organic matter, which may be a significant component of the dissolved matter in some lakes.